Yeah, thank you very much for the introduction, Anita, and thanks also to the organizers for inviting me to this very nice workshop. My first time at IPAM, and I hope so. It should be. Okay, I try to speak louder. Yeah, so my first time at IPAM, and I really like the format, a great conference. All right, so equity in transportation systems, or let me call it fairness in this talk, that's a difficult subject because there are several groups of actors involved in a transportation system, and it is somehow impossible to design the system in such a way as to optimally suit everybody's needs or wishes. So, and then seems that we can only minimize the dissatisfaction and distribute it somehow in a best possible way. However, the preferences of the actors and also the way in which fairness should be measured, that is not so clear, and therefore different approaches have been suggested in different contexts. And so I thought I just talk about three in which I have been doing some work, and that is the fair distribution of work to the employees of a public transit company, competitive access to railway infrastructure for train operating companies, and the design of fair ticket prices for a public transportation system by means of cooperative game theory. So let me start with my first topic, that's fair distribution of work to employees of a public transport company. And we have been working on that with Thomas Breugem, Christoph Schulz, and Thomas Schlechte as a part of Thomas's PhD project when he spent a year at Zuse Institute, Berlin. So to get you set up, as Anita told us yesterday, the distribution of work to employees is done in two steps, right? So the first is called duty scheduling. It's about the construction of anonymous shifts of daily work, which is then in a second step of crew rostering, arranged in some scheme that tells who is doing what kind of work at what point in time. So on this slide, we see on the left some statistics about duty optimization or crew scheduling at Berlin's public transportation company, BVG, to give you an idea of the size of the problem. And here we see a Gantt chart of some of these duties, and we see that most of them, so typically they consist of two parts, with a break in between, and ideally we would like all of these, so the break is unpaid, and ideally we would like to have all of these duties to last about 8 hours of duty time or paid time. And we also do not want too many of these split duties with these super long breaks in between. But if we, now this doesn't work. We go to the next slide. Oh, I see the slide here on the computer, but not on the screen. So hopefully it will come up. What can I do? Nothing, just wait. Then maybe I continue, hoping that it will come up. I see it here on the computer, but not on the screen. But when you optimize kind of for efficiency, then there is, of course, now maybe it will come back now.
It didn't.
Here we are. Yeah, but when we optimize for efficiency, then there is, of course, a tendency to produce these long duties here, and there is also a tendency to produce a lot of split duties here, because they are best suited to cover the peak demand hours in the morning and in the afternoon. And we can explore now the trade-off between getting rid of the number of split duties and the cost of the duty schedule. And we could also explore the trade-off between adjusting the average paid time to the goal that we want to have. And this can be done However, it can be done for the paid time better than for the number of split duties, and that's very expensive, and that's why it's rarely done in practice. So what most public transit, so this is an example here, so what most public transit companies are doing is they optimize for efficiency in duty scheduling and then deal with fairness in the subsequent rostering step. So what we do there is, when we have reduced the duties, that we have it here, then we assign them to this kind of roster scheme here. And this works as follows. So let's suppose we have some kind of duties here that we
Recording in progress.
We have to do on Monday and on Tuesday and so on. And then we arrange them in such a way that some employees working on these 5 days in the first week, and then working on these duties in the second week. These would be the duties in the third and fourth week, and then something that remains in the fifth week. And after that, we would start with this scheme again in the first week. And then this roster scheme can be operated by 5 employees, or maybe 6 if we also account for holidays. And then nobody can complain about unfairness because everybody who's working this roster is doing the same work in the long run. Yeah? So, and that's some kind of fairness. That's what they do. Now we can arrange the duties in a nicer way, such that we have 1 week of work as 1 row of the roster scheme, and that's the way that we typically look at it. Now, the most fair thing that we could come up in this context is then to have one, let's say, gigantic roster scheme for all of BVG with 2,000 rows, and then it would take about 40 years to cycle once through the scheme, and that would, of course, never happen in practice. And it would also make no sense, right, because the crews are stationed in different depots, and that's one reason why we are forming much smaller roster groups in practice. Like here in this example, we have these 2 roster groups. And since we have already established some kind of fairness for the employees of every group, then the matter of fairness would be to think about the assignment of work to the individual roster groups. And one can measure fairness with respect to different attributes. For example, we could look at the number of late and night duties that the people in some roster group have to serve, and then we would see, for instance, that this first roster group here has night duty, late, so a lot more late and night duties than this second roster group here, which has mostly early duties, yeah, and then maybe we think that's unfair or not, yeah. So and then we could try to have more balance in this assignment to establish a higher level of fairness. But then if we do that, it might happen that we have some weeks like this one here, yeah, where we work on 6 days and then even 2 more days in the next week. So long sequences of work and maybe also long sequences of late and night work successively. And that would be then maybe very fair, but also unattractive for the employees. Yeah? So there is a trade-off then between fairness and attractiveness of the roster, or let's say, since everybody has a different opinion about that, between perceived fairness and perceived attractiveness of a roster. And we could measure perceived fairness as the spread between the maximum and the minimum value of some attribute or some indicator that we measure over all the roster groups, yeah? And we can measure perceived attractiveness as the thresh or surplus over some attractivity threshold that we must, of course, come up with. Yeah? And then we can optimize for the attractivity here at some budget of the fairness, and typically in practice one considers different fairness levels like, say, extreme, high, medium, low, and poor, and then see what one gets out of it. So this integer program that I've shown you here does not solve with Gurobi for large instances, and that's the reason why we designed a special heuristic to do that. And just very quickly, what the thing does is we first compute a solution for the most tightly constrained scenario of, let's say, extreme fairness. then the solution is improved and then adapted to lower fairness levels, so kind of to come up in a more quick way with several good solutions for different fairness levels. And since this, let's say, path of work through the roster is like a tour through all the duties in the roster, it's like that's like a traveling salesman problem. One can use a Lin-Kernighan type variable depth exchange heuristic to do that, and that's what we developed here. So we call it DEX. So we applied this method to data for some depots of the Dutch railway operator NS Reisigers here. And so these are the data. So we have 10 data sets here. So these 4 ones here, these are small data sets that can be solved to optionality with integer programming. So we can use that for benchmarking the methods. And then we have here 6 more larger data sets. And if we look at the employee groups here that we have, so the roster groups, we see that we have here in these instances 1 or 2 groups of 12 and 12 people here in this instance that do only early duties, some that do only late and night duties, and some that do mixed duties. So you see that coming up with something that we would consider as reasonable fairness levels is not so easy. So it's not that fairness means that everybody is really doing the same thing in every roster group. The reason for that is that so at some point in your life, some employees need a regular daily schedule because they have to bring children to school or something like that. So and then you hope that maybe at some point you are in this group here in the early group, and then maybe later on you go to the mixed group, or maybe you need money, then you go to the late night group because then you are compensated for that. That's how it works. All right, so let's look at the small instances here. And this slide here just shows us sort of the 4 instances and the different fairness levels, and we can compare the heuristic in the different phases here to the optimal solution that we can produce with the IP, and then look at the gap between the solutions, and we see that the heuristics works mostly very well, except maybe for this instance here. It does not work so well. That's because it's a heuristic. So if we look at the 6 larger instances, we can see that if we start with the most extreme fairness levels, we can increase the attractivity here substantially, of course at the price of reducing the fairness level with this heuristic. Okay, and that's what's done in practice, more or less by most public transit companies, maybe not exactly like in this approach, but kind of similar to this approach. In the airline,
I have a question here.
Sure.
So in some earlier talks, I think yesterday, there was a discussion about the actual fairness in sort of an inductive way versus the perceived fairness by the people, and these need not always be the same. And one argument was when you optimize for the people rather than the employees, that the objective fairness has a real point, right, for multiple reasons. But here in this case, when you optimize for the employees, I'm wondering, is the objective fairness actually of importance, or is it not that only the perceived fairness really matters?
Yeah, so it's exactly what you say, the perceived fairness. So this is very different from company to company. So kind of this is a negotiation process. So what typically happens is that the company has some way of doing this, and then people start complaining, say this is unfair, and then kind of a negotiation process starts of how the rosters can be improved. So in the Netherlands, they have this is called sharing sweet and sour. So, and then, of course, the question is, what does it mean, sweet, sour? How is it shared? What is the fair way to do that? So, and then people kind of will explore the scenario, look at the solutions, and then come up with, so kind of per company or maybe per depot, with different ways of what these people in these roster groups, these employees think what is the right.
In an earlier life, I worked as an EMT for the Red Cross, and there I was also working night shift and so on. And one of the things that was important for perceived fairness was, is it a simple rule that can easily communicate? And once you do solutions like that, that sort of goes away.
Yes.
Right. And I'm really wondering how the people on the actual roads or the bus feel about it.
I cannot give a kind of. I think there is no general answer to that. So For instance, these split duties, yeah, this is something that people in Germany, for instance, German bus drivers don't like at all. Yeah, so what they want to have is they want to have kind of the period of time in the day that they work. They want to have this compressed as much as possible, so short as possible break. Yeah, while for instance, I learned that in France or parts of Switzerland, people want a long break to have a meal at lunch. So and then it was kind of completely different. Another thing that I was not discussing here is attractiveness of a roster can also mean that you do something different on every day of the week. As you don't want to drive the same tracks every day. Yeah. In some companies, in other companies, they say, "Oh, but then I have to prepare every morning, and I don't want that. I want to do." So this is completely different and depends on the individual preferences of the people. Yeah.
Thank you. Yeah, interesting.
So can you also consider having different compensation ranges for different?
Yeah, this is what's done here because, so I mean, nobody would go to this late and night roster group if they would not be compensated for that with money. Yeah, but the kind of this coming up with these levels and these compensations, what is considered, how that is a complicated process.
I'm wondering why not do it the other way and have individual drivers bid on or pick, so like either by seniority or by lottery assigned slots, and then you pick your schedule, and this week you get to pick whatever schedule you want, so you pick the best one, and next time you have a worse schedule or something.
Yeah, that is done in the airline industry. So like sometimes by seniority and sometimes by preferential bidding, as you are suggesting. That's another way of doing it. But I don't know any bus company that does preferential bidding, so they do it like this. But that would be also a valid approach.
But I guess is there some reason? Because I know it's pretty common in the airline industry. Is there some reason why bus companies don't do it, or is it just standard service?
Yeah, I mean seniority. I think they say seniority is kind of for somebody from Europe. That's kind of a strange concept. Yeah. But preferential bidding, I think that would be something good. I think the main problem there is that you then have to account for a lot of budgets. So for instance, who is going to work at Christmas or something like that, and you must account for that over several years, and that kind of takes away some freedom from the scheduler to assign people to do some work they maybe might not want to do. And they say, okay, but I still have this many credits and I don't want to do that. And so kind of, I think this rostering, that's kind of a compromise between this very free type of preferential bidding and an approach where more somebody tells you what to do. Yeah. Mm-hmm.
Could you try to price the unfairness, like you compensate people who are inconvenient? Would it be possible that it's actually cheaper than you have to rearrange your schedule?
You mean like computing some kind of prices from dual variables or something like that?
If you inconvenience somebody, you just pay them.
Yeah, I think that would be possible. But again, I don't know of any company who is doing that. So what they do is they have kind of from history, they have some levels of fairness and preferences that they know, and then they try to improve a little bit on that. And they say, okay, next time we try to have a bit more fair in this respect. That's how they do it. But I mean, it could, of course, be done. Mm-hmm. All right, yeah, so preferential bidding, this auctioning, that's my transition to the next topic. Auctioning is also a way, or can be a way, to reduce unfairness. And we have been working on that in the context of, let's say, fair access to railway infrastructure for train operating companies. And that was the topic of Thomas Schlechter's PhD thesis, and Anke Reuter was a student that was working on that. And so the setting is as follows. So if you want to run a train in Germany on the network, then you have to order the train or a route for the train through, for instance, this web portal. That's one option to do it. And then if many people do that and everybody gets what they want, then that's fine. But if that is not possible because we have a conflict between two trains, yeah, then what is done that the network operator starts a negotiation process in which he tries to convince the involved parties to change their requests in such a way that everything can be accommodated. Yeah? And only if that is not possible, then the German law prescribes that some kind of, it's an auctioning method essentially, has to be carried out in order to resolve the conflict in favor of the party that has the highest willingness to pay. Yeah? And that never happens in practice. And that is why the network operator tries to make that sure, and then they say this is not really necessary because they always manage to make everything possible, kind of from their point of view. But the economists in this, so this was an interdisciplinary project, and the economists argued that maybe this negotiation process is not as fair as it might seem, and that it is kind of puts new train operating companies and also small ones at a disadvantage in comparison to, let's say, the very big company that is in this network. So, and then the idea was to resolve these conflicts by means of an auction. So here is an example for that. So we have here a route, and then several trains that we want to run. Time is going downwards, and associated with each of these trains that somebody wants to run is some bid value here. And then we can look at, for instance, here, let's say these two trains here, they are not in conflict with anybody else, so we can just assign these bids, that's okay. Then we have these two bids here, which are in conflict with each other. So this fast train here would run through this slow train, but the slow train has a higher bid, so we would grant that and reject the other. And this type of situation, that is also what the people who made this law about this auctioning process had in mind. But of course, there can be much more difficult situations like here, and then it's not so easy to see anymore where the conflict actually is. And then we can do different things. For instance, we could assign first this train here, because this has the highest bid of all. That would be kind of a greedy approach, but then we can grant only this one more, and this gives us some total value. And if we choose another solution, we can have a better value, or this one would be the optimal solution. And what we actually see is that what we are solving here is a set packing problem, of finding a best possible combination of train routes that are not in pairwise conflict. So that's a combinatorial optimization problem. And if we introduce some flexibility, let's say in time, to move the routes a bit forward or backward, or maybe or even in space, to take a different route that might be in particular an option for a cargo train, then we can have an even better solution, so maybe like this one here. So that's the problem that we then have to solve in this auctioning approach, right? So it's a combinatorial optimization problem. We have all these requests here for running trains with some flexibility in them at some discounts of whatever valuation our train operating company is giving to them. And we want to pack these train parts in such a way as to realize the combination that has the maximum overall value. And maybe just very shortly about the mathematics of that, there is a way to deal with the conflicts of trains here, not by forbidding them, but by looking for every track segment here of combinations of trains that can be run without a conflict. And these combinations, feasible combinations on an individual track segment, we call them configurations. So they correspond to a path in this type of digraph here. So where one train trip over this track is connected to the next feasible one. And then these train paths and also these feasible track configurations, they can both be priced using shortest path methods. And then this gives a very, it's a big but kind of conceptually very simple combinatorial optimization problem here, an integer programming formulation to solve this type of track allocation problems. That's what we developed in this project. And with this method, we could at that time solve problems involving about 1,000 requests for train routes in, let's say, half a day or a day. And in an auctioning framework, of course, this then has to be done multiple times because the train operating companies would submit some set of bids. Then we would kind of compute the optimal combination, and then the bidders inspect the solution and they say, oh, okay, I did not get this and that I wanted, and then maybe I raise the bid or I change the bid or I submit a new bid, and then we do it again until no more bids are coming. And since this can, of course, take a long time, then one usually adds some rules to this auction. For instance, that bids have to be incremented by a minimum amount of, let's say, 15% or so, such that this auction is not running forever and getting to an end quick. That's the idea of running this track auctions. And why is this a good idea? So you can argue that this type of auctioning resolves conflicts in a kind of way that in favor of the bidders with the highest willingness to pay, and that is somehow economically efficient and leads to some kind of welfare maximization. It also maximizes the revenue of the auctioneer. It reveals the bidder's willingness to pay, and it can also, for the auctioneer, point out parts of the network where additional capacity would be useful to have, because you have more demand, and this could kind of guide an investment decisions for investment into the network. And if that works, then economists argue that it's usually a good way to run a system. And some successful auctions that are usually mentioned in this context is, everybody knows eBay. Then there is the famous Sears and Roebuck trucking auction. It's maybe already a little bit questioning if the spectrum auctioning is really a good idea. And something like this has also been done in Britain in order to distribute regional monopolies in the British railway system. Okay, so in order to explore this idea, we set up a test network here as a part of the German railway system between the cities of Hanover, Kassel, and Fulda. So we call it the HKFU network. So here are some statistics on that. And when we looked up the timetable for this network for, I think it was a 4-hour time window, then there were 322 trains running in this network. So that would be kind of our reference solution. And what we now try in this auction is we come up with some additional demand by creating a model for artificial companies and trains that they would submit and trying to estimate in the best possible. So this was a big project. We had 2 economists in it and 2 railway engineers. So then they thought about what kind of additional trains could we run, what would be the revenue that we can generate with that, and what would be the willingness to pay for such a company to enter bids into this auction. And then what we did is we took these trains of the reference timetable and then add additional requests, let's say for high-speed trains, individual high-speed trains, or also bundles of synchronized high-speed trains, something like every 60 minutes or so, for regional express trains, for regional trains, and also for commuter trains, or maybe everything together at once. And we can see the results here. And what we also did is we looked at 2 different scenarios. So one is where the willingness to pay for a bid is something like the estimated revenue that we can gain from this trip. So there's a revenue-oriented model. And then we do another one where the maximum willingness to pay is the price in the current pricing system, in the track pricing system that's labeled TPS here. And that's the maximum willingness to pay there. And then if we first try to schedule the reference timetable in this setting, then we find out that it is not possible in both settings to schedule everything of the reference timetable because of some data problems. So this is really a problem in railway modeling to get it completely right. And you see that we could schedule only 302 and 310 trains in these different settings. So what we see is the revenue here is typically larger than the prices in the current track price system that the German network is currently charging. And this means that fewer bid increments are going on, and then the number of auction rounds here in this track price system setting is generally smaller than in the revenue setting. What we also see is that this type of auction here favors high-value, high-speed bids on high-value, high-speed trains, and in particular, if we have bundles of synchronized high-speed trains, because it's very hard in this type of auction to get rid of a high bid on several high-speed trains at once, because you must have a kind of a completely fitting combinations of bids by several other bidders that kick this one synchronized bid out. So that's a problem. So that is true for these high-speed trains, and to a lesser extent also for these regional trains here. But in total, so a green cell here in this table means that we have scheduled more trains than in the reference timetable. Red means less. So we see that in total we can schedule some extra trains. That is possible by this type of auction. So in this sense, it's good. If we look at the revenue,
It seems that it's maybe fair from the operator perspective, but there are impacts on the passengers, of course, tremendously.
Sure.
And it very much depends on the pricing scheme in your train network, how much an operator can bid. And that pricing scheme, I assume, is set by the government, where for high speed you may make charge more than for slower trains, where there are price caps and student reductions. And
right, yeah. Yeah, of course.
so you have very unfair competition in a fair auction, I would say. So how do you handle that? Or maybe is my description completely wrong?
No, I mean, what you say is completely right. This is it's a difficult problem. Yeah, you can try to take all kind of aspects into account, but this is already quite difficult to solve this combinatorial auction. I think the only answer that I can give is we try to do the best that we can. And this study was not kind of intended to kind of produce a timetable that you would really implement. It was more like kind of looking at if such an auctioning mechanism can work at all.
So how did you generate the prices that different services were willing to offer?
Well, so we implemented a demand model. So we tried to estimate how many passengers would go between different cities, and then how much would you kind of be willing to pay for going on a train, let's say of a certain category, and that gave some estimate of a revenue that you could make by offering an additional train. That's how we did it.
So there is some link with demand, which is a little bit shaped maybe by the price.
Yes, I would, yeah, right.
This might be related to what you just said, but as a consumer or passenger, it's really useful for me to know that like every hour and 4 minutes past the hour, my train to Hamburg leaves. And so I don't have to think about and so can you, does that rely on each train's operator sort of really pricing that into pricing the importance of this train leaving at 4 past the hour or something into their bid? Or is there a way to guarantee that or provide that and avoid sort of very maybe efficient but convoluted schedules for the
Yeah, so the approach here in this auctioning scheme was that the train operator kind of has to take care of that. We always had this discussion whether kind of in a day where everybody has a mobile phone and can look up departure times, whether it's kind of really necessary to know the exact time of departure, or whether you cannot just look it up and say, okay, it's about every hour something is running on this track or not. But maybe I think I should answer your question in a different way, because kind of at the end of the project, it was kind of the feeling of us who did the project that this kind of let's say the great auction, where the train operating companies try to come up with some bids and then something more or less random comes out of the auction, that's not the way to do it, and that it would be better to have the network operator think about that in advance and offer some, let's say, predefined routes on which the bidders can submit their bids. and that would probably be a better way to do it.
The network operator could sort of put that in this.
Yes. So, and they observe the demand, what people want to do, and then changes their offers in this way. All right. Yeah. Okay, that was this. Then I mean just one more slide where you can look at the prices per kilometer, and then again you can see that this current track price system here in this setting somehow favors the high-speed trains over a, let's say, revenue-oriented setup. All right. Okay, then let me come to my final topic, design of fair ticket prices in public transport by means of a cooperative game theory. That was the topic of Nam Dong Hwang's thesis that I supervised together with Martin Gottschel. And let me explain it here on this example here again of the Dutch intercity network, that we do that with a data set by Michael Bussig, which is very popular in this area of public transit network design. It has this network here as an OD matrix, distance matrices, and some more stuff that we don't need for this project. There is no price information in this data set, but we queried that in the internet at that time, and it turned out that at that time, at least, it was it's a discounted distance tariff that they were using. And yeah.
Question for the colleagues. There is no railway connection between Utrecht and Breda, but it shows in your map.
Yeah, this is.
I would have wanted it to be there because I lived close to Breda.
This is, well, okay, this is from 1998. Yeah.
But
So
it's never been a railway track.
this is not, well, it's kind.
I mean, you can get from Breda to Utrecht by train, but you have to switch trains. And
Yeah.
also, I'm confused by your graph. Not important. Go on.
I was not designing this. I mean, everybody is using this.
Really?
Yeah.
Interesting.
All right, Anita, you have used it also. We are. It's well, it's. We used it for a lot of studies. Yeah. Okay. Anyway, even if this connection does not exist. All right. Okay. So the question is, are these fair prices? And the way that we want to study that is, as I said, from the point of view of cooperative game theory. And the groups of people that we are looking at are those that want to go from a certain origin to a certain destination. So the origin-destination pairs are the players in this game. And they are currently all together in the system, in the grand coalition. And what a particular group of people could now think of is, let's say they form a subset of these OD pairs, a sub-coalition, and then they look at the difference between how much it would cost them to set up their own system and compare that to how much they are currently paying with some prices that we call X. Yeah? And then we could look at these differences here, maybe just the absolute difference, or we can divide by the number of players, or we can look at relative to the cost that they have, so kind of a weighted difference here. And if this is negative, so if they pay more than it would cost them themselves, then they might say, okay, we are unhappy with the current pricing system. And of course, what we would like to ideally have is we would like to find prices that cover the total cost, yeah, and such that nobody pays more than it would cost them to do it on their own, so that these excesses here are all non-positive, yeah. What? Okay, they set up their own public transportation system. Yeah, so we will solve a line planning problem to do that and run kind of their own trains to satisfy this demand. Yeah, so nobody wants to pay more than it costs them currently in the price. Otherwise, they are unhappy. That's the point of view that we take here. Ideally, we want to find prices that this never happens. Yeah, but of course, and these prices are then in the core of this cooperative game. But the core is typically empty. For this type of game. So then the only thing that we can do is we can look at the coalition that is worse off with respect to this measure, and then minimize the loss that this coalition has or maximize the excess. Yeah, so the excess is negative, so we want to have it as high as possible. And if we do that, then we compute prices in what is called the least core. Yeah? And if we then do it in such a way that we first minimize the loss of the worst of coalition and then of the second worst of coalition and so on, then we compute a set of prices that are unique, and that's called the nucleolus of the game. What we want to do in this setting also is we want to have some control over the coalition formation, and we also want to be able to stipulate additional constraints on the prices. So we will see later why we are doing that here in this talk. And now what we want to do is we want to find some cost allocation method here that is good for this kind of cost allocation games. And what does it mean to be good? What kind of properties would we have? Of course, we would like to have that the total cost is covered. That's called efficient. We would like that no coalition has an incentive to leave the grand coalition, so that everybody stays in the system. That's coalitional stability. We already said that core prices would be good because then nobody has an incentive to leave. Maybe we would want to have that when the costs of the system changes a little bit, the prices also only change a little bit. That would be some kind of stability of the prices and so on. And we could now think of some cost allocation methods. For instance, we could charge every individual his individual cost, what it would take them to do their own system. That would be a fixed price cost allocation, but that is typically, so then the prices are too high because we have no effect on cooperation in there. So then this is not efficient and the solution is not in the core. We could distribute the total cost with respect to the ratios of some individual cost with respect to the sum of the individual cost. That would be proportional. That's not coalitionally stable, and it's also in general not in the core. We could use these least core prices that are introduced, but they also have their disadvantages. And in fact, one can prove that one cannot have kind of cost allocation methods that for all of these cost allocation games always has more than 2 out of these 4 properties and some more that you can think of. What one can do is one can find a point in the least score of this game in polynomial time, with respect to some complexity model, because maybe I'll show it again here. So this least score here is, we can compute it by solving a linear program here, which has these exponential number of coalition constraints here, and we have to be able to solve that efficiently, and then we have an oracle polynomial time algorithm. All right, so if we have now computed whatever price system, or come up with it in some way, how do we get a feeling for it, or how do we compare it? And we do this by looking at this type of Lorentz type curve here, by looking at all the coalitions and looking at the losses of these coalitions and plotting them in an ordered way. So, and then, for instance, this is this diagram here for distance prices. And actually, we have to sample the diagram, because we cannot compute a point for each of this exponential number of coalitions. There's a way to do that in some representative way. We can also do that for comparing 2 price schemes, by plotting the prices of the second pricing scheme in the order of the first, or maybe by plotting them in their own order, and then we have a comparison here like this. There's now one, so we are suggesting to compute least score prices here, and there's one more thing that we want to have is we want to compute not the nucleolus of the game, kind of to find a Lexi-max solution of prices, but we want to find a solution in the least score that has the least possible deviation here of prices with respect to some reference prices, which would be the distance prices here, such that the ratio for each individual player or each individual OD pair is as small as possible, because that is the first thing that you would look at. If somebody suggested a new price system, then you say, okay, how much more do I have to pay in comparison to what I had to pay before? And that can be also computed. That's a kind of iterative application of this type of cost allocation scheme. The cost was already asked. What is the cost of a sub-coalition? It's the cost of establishing the service on their own. So, and we do that by solving a line planning problem, like Anita showed it yesterday to us. So the people in this sub-coalition here induce some demands. So in passenger volume and also in frequencies, if we want that, and we want to satisfy that at a minimum total cost by establishing routes at some frequencies. And actually there's a term here that tells us how many vehicles we are using in each train on this network. So some kind of cost model here, a line planning problem. In order to solve the separation problem for the coalition constraints, we also have to find the coalition. And that can be done by extending this model here by additional integer variables that generate these demands here. So then the line planning problem is a bit more complicated, but it still can be done. So in our setup now, we have this more or less realistic or model of the Dutch railway system, and we have a lot of OD pairs here. We did not consider all of them. We threw away those which have very low demands and kept the 81 OD pairs with the highest demand. As the reference price, we use a distance price, or price per kilometer for every passenger, that is scaled in such a way as to cover the total cost. So then for this new least core prices that we want to compute, we want to have some of the properties that Anita already also explained to us yesterday. So like some kind of monotonicity properties, that it's not so if you would not like to be able to split your trip, or do tricks like that, for instance, like this here. And we will later on also consider another constraint that limits the deviation of the new prices from the distance prices to some maximum factor of k. We'll see that in a second. And as the weight function, we take the cost so that we look at relative savings for every coalition. So that seems like the most natural thing. Okay, so now if we, with this setting, compute these least core prices and compare it to distance prices, then we obtain a diagram like here. If we sort it like this, and then we see that these distance prices here, that there are some coalitions that have significant losses, like the maximum loss is 25%, and even worse, that is something that we call it the Randstad coalition. So that's kind of a group of OD pairs in the center of the Netherlands, so which connects all the major cities, and they have the highest loss. While if you look at the least core prices, there are some coalitions that have a small loss, but it's only 1.1%, so almost not perceivable. So, but if we, so that seems to be good. But if we compare the least core prices now to the distance prices that we have before and look at the ratios of these prices, then we have two OD pairs here where people have to pay a lot more than before. So the highest factor is 14.4, which is really a lot. And that is for the OD relation between Den Haag Central Station and Den Haag, I forgot what HS means.
Maybe because this is all beyond me. I don't understand how the prices are established. It's game theory, you said.
It's
right?
game theory, yes.
So
what you try to do is you look at a price. So maybe I go back to this game theory slide. So what we try to find is a set of prices, non-negative prices, that add up to cover the total cost. The total cost is if everybody is together in the network and we solve the line planning problem for the grand coalition. That gives us some cost.
We say to that in the game, all
That's
the
the
all the
total
players
demand in the
together
game.
have to deliver that result.
Now, that is a grand coalition,
Okay.
has this type of cost. And we want prices for each of them that the total cost is covered. And so the system is run by ticket prices. That's the setup here. So, and then we think about what ticket prices should people that go between a certain OD pair have to pay. And we say each OD pair can team up with some other OD pairs and say, if we would run the system on our own, then it would be cheaper for us than the ticket prices that we currently have to pay, and then we drop out of the coalition because we have a loss. And we try to minimize the maximum loss for all, for all coalitions. That's how we do it. And we compare that to the distance prices. All right? Okay. And then we have here this, so this is then what comes out. Yeah, so we see that these losses here for per coalition can be minimized. So there are some coalitions that have a small loss. There are a lot that have a big gain, yeah, that pay a lot less, like 80% gain. Yeah, so very good for them. So here in these distance prices, that there are some, according to this cost model, have to pay more than if they would kind of do the system on. We will see in a second what it means. Okay? All right, so these two OD pairs that have to pay a lot more. There's this one pair between this very short trip here between the two stations in Den Haag. And the reason is that this connection is used by no other OD pair. It's only used by these persons that want to do this very short trip. And so I think it's debatable whether this is the right price or not. Yeah? And then there is another one. This is a factor of 12. Yeah? All the others have increases of at most a factor of 3.7, which is still a lot. Yeah? So that's why we introduced this additional constraint that we want to compute prices in such a way that the increase is at most some factor k, and we set k to 3. And if we do that, we see that these least score prices change a little bit, but almost not noticeable. And if we compare these new, let's call it bounded least score prices to the distance prices, then we see we have the same properties as before, and the maximum increase factor is now actually lower than 2. It's 1.89. So if we look now at the OD pairs with the biggest differences, like the kind of the best 15, yeah, that have to pay less. Yeah, so there's, then let's look at where they are. So we have Arnhem and Zevenaar. This is this one here. Then we have Amsterdam-Roosendaal, Breda-Eindhoven, Roosendaal-Rotterdam, Roosendaal-Zwolle, Eindhoven-Den Haag, and so on. And what you can see, so I have to be, and that was too much. So what you see is that there is a certain part of the network, yeah, where people benefit. And if we look at the worst 15 relations, then we see that it's this one here from Lelystad to Zwolle, then this here, Hengelo, and the one that we saw before between the two stations in Den Haag. This part here of the network, there's not much going on, also in this branch here. Then in this part down here, and there. So if we compare it, then we see that there are some parts of the network here, here, and here, yeah, where people would have to kind of pay more in this least score price system, while these people here in the center of the Netherlands, they would benefit from these least score prices. So, and as it's currently the other way around, is what it means is that in kind of in this type of cooperative game theory setting, the people in the center of the Netherlands are subsidizing some trips here in these parts of the network. Yeah. Mm-hmm.
Doesn't it seem to be a very complicated way just to measure the cost per passenger vis-a-vis how much the passengers are de facto paying, and that's the gap you get?
Well, we don't measure the cost per passenger. We compare the cost of establishing a system for a subset of the people to what they are currently paying.
would that be so different from, maybe the train runs on a longer track, but you ride for 10 kilometers. And,
Yeah, as you see here.
It costs X to run that 10 kilometers in the train, and there's only 5 people, so it's very expensive for you.
Yeah, that is what's probably going on here, yeah.
Exactly, so why make it such a complex game theory thing when you can just calculate it very straightforwardly?
That would also be
It is more impressive, but...
kind of, why? Yeah, because, I think there is no, what I want to say is there is kind of no, let's say, way to do that in a best possible way, or a way that you could say you have to do it in this way. And that is just one approach, yeah, that can help to identify maybe weaknesses or unfairness in this kind of system. You can also do it in another way, yeah. Yeah?
You assume all passengers have the same maximum price that
Yes, all passengers that use the same relation have the same price to pay. So there's a different price for every relation. Does that answer the question? Yeah?
So one underlying assumption behind this is that you have this notion of transferable utilities, right? That's the point of this core concept. But if you think about people who live really far, oftentimes they might do so because of, I don't know, housing costs or something.
Mm-hmm.
And so for some people, like, even though they're really far, they really value being able to move from point to point B. But a scheme like this one would charge people more so because just based on the distance, even though their utility is really high for taking the service. So I guess my question is, what do you think about applying core-like concepts in like transit design when you have this notion that utility, like if I gain, it's not easy for me to send my utility to someone else, because my utility is not necessarily only based on the cost of building the system, but rather what I reap from it, from being able to access something.
Yeah, I think what you mentioned is a good example, actually one that we had in mind when we started this out. Exactly the situation that kind of people move out of the city, let's say far away, to buy some real estate, and it's much cheaper. Yeah, and then once they live there, then they say, okay, but now we need public transportation. Yeah, for let's say the same price per kilometer as other people, and then all of the public has to pay for that. Yeah, in order kind of to subsidize, in a sense, this transportation demand. And the question is that fair, or should not these people that move far outside pay for the services that they want to use? And in this core concept, this would exactly come out, because then the people in the city center would say, we better set up our own system, and then cheaper for us, we can charge smaller prices.
Time is running up a bit. How many slides do you still have?
Only one. My advertisement slide for GRIPS 24. So we do it every year. And this was from last year. This year we don't have a project in the mobility lab, but probably next year again. So if you want to send some student to ZIP to work on a project like last time we had e-bus scheduling, then consider that. And it's not only about work, it's also about, so here's Christian, here's Nicole, here is me. All right.
Very good. So we have one more question, and then we first thank Ralf, and then we come to this question.